Good day, everyone. This is now the last chapter before our prelim exams. We'll now be discussing deadlocks. Now, several processes may compete for a finite number of resources. A process requests resources. So, if the resources are not available at that time, the process enters a waiting state. Sometimes, a waiting state process is never again be able to change state because the resources it has requested are held by other waiting processes. This situation is called a deadlock. So the deadlock can also be drawn from a law passed by the Kansas legislature during the early 20th century. It is said that when two trains approach each other at a crossing, both shall come to a full stop and neither shall start up again until the other has gone. Now let us try to illustrate. So if we have this figure, okay, so may crossing daw, and that there are two trains. Ano ba drawing ng train? O, ganyan. So, if there are two trains on this crossing, okay? So, syempre, we have only one resource, itong daanan na to. So, kung ang dinadaanan nila ay isa lang, then this is a resource that is non-shareable. If it is non-shareable, therefore, only one will be accommodated. It is either train 1 or train 2. Now, for then, to solve the problem, para magamit po yung resource, one of them shall give way. So, kung mag-give way yung isa, either T1 or T2, then this resource will be now available. Okay? So, yun yung illustration on Kansas legislature. This can also be compared to, say, meron tayong dalawang resource kasi it's not at all times na iisa lang yung resource like this road. So, kung halimbawa, meron tayong resource na pencil, okay, and then the papel. So, you have R1, then you have R2. Okay, this is a resource, a ball pen, or a pencil, and then a paper. Ngayon, you have two users. User 1, user 2. So, kailangan, itong mga resources na to, multiple resources, will be used by one user only. Halimbawa, kumuha ka ng quiz. So, yung quiz, kailangan mo ng para makasagot ka ng papel at ballpen. Ngayon, kung ang ballpen ay nakuha mo, eto, it's useless without the paper. Kung yung paper naman ay nandito po kay user 2, it's useless kung wala itong ballpen. So, para makakuha ka ng test, you have to await na matapos ni user 1, etong isusulat mo, ballpen, pag natapos niya, tsaka ka dito magsusulat. Ganon din si user 1. Para magkaroon siya halimbawa ng papel na may masusulatan siya, user 2 will voluntarily give this resources. So, isa lang ang pwedeng gumamit ng dalawang resources na to. So, this is also another illustration of a deadlock where we have two resources that will be held by a user. Now, in this chapter, we describe methods that an operating system can use to prevent or deal with deadlocks. Although some applications can identify programs that may be deadlocked, operating systems typically do not provide deadlock prevention facilities, and it remains the responsibility of the programmer to ensure that their design is deadlock-free. Okay. Ano po yung ating pag-usapan? We have under deadlocks, the subtopics are here. Then we have the goals for this chapter. Okay. Tayo mag-next. We have system model. Ano-ano po yung system model sa deadlock? A system consists of a finite number of resources to be distributed among a number of competing processes. The resources may be partitioned into several types or minsan sinasabi nating classes, each consisting of some number of identical instances, like CPU cycles, files, input-output devices are examples of resource types. Okay? Yung process naman, a process must request a resource before using it and must release the resource after using it. So, kailangan ko ng ballpen, i-request ko si ballpen. Pagkatapos kong gamitin si ballpen, i-release ko si ballpen para ito ay magamit ng iba. A process may request as many resources as it requires to carry out its designated task. Well, obviously, the number of resources requested may not exceed the total number of resources available in the system. So, in other words, a process cannot request 3 printers if the system has only 2 printers. Now, under normal mode of operation, a process may utilize in only of the following sequence. Ano-ano to? So, we have request, okay? We have use and release. Isa-isahin po natin. Request, ibig sabihin, the process request the resource. If the request cannot be granted immediately, for example, if the resource is being used by another process, then the request process must wait until it can acquire the resource. So, yun yung pinakaunang step. Kailangan niyang i-request yung isang resource. Next, use. The process can operate on the resource. Pwede na siyang maggumamit after the request is granted. For example, if the resource is a printer, the process can print on the printer. Lastly, we have release. Okay, tatlong step. The process releases the resource. Tapos niyang gamitin, yung pinaka-next step is to release the resource. So, the request and the release resources may be system calls. Examples are yung request, release, o di kaya open, close file, allocate, free the memory. Those are examples of release. So, please also be familiar with the symbols here. We have R for resources. Okay, so pag nakikita natin mamaya sa figure, if we have R1, R2, we have the resources. Resources, examples are CPU cycles, ito yung mga types, memory space, also input-output devices. Si resource, meron po siyang instances. Okay? Like, if I have a resource, I have a ball pen, then, if I have only one ball pen, I have one instance of that ball pen. Now, this will be illustrated on the next figure. Okay, so, wala palang figure, concept pa. So, we'll have the deadlock characterization. Paano natin malalaman that these are conditions of deadlock? So, we have four consideration. Una, mutual exclusion. When you say mutual exclusion, at least one resource must be held in a non-shareable mode. So that is only one process at a time can use the resource. If another process requests that resource, the requesting process must be delayed until the resource has been released. You cannot call your friend's cell phone if your friend is currently accommodating a call. So, kailangan niya munang i-release. Next, we have the concept of hold and wait. Okay, so kanina, we have mutual exclusion. Next, we have hold and wait. A process must be holding at least one resource and waiting to acquire additional resources that are currently being held by other processes. So, you have to wait until your friend finishes the conversation on a phone call. Next, no preemption. Resources cannot be preempted. Hindi siya pwedeng pahintuin. That is, a resource can be released only voluntarily by the process holding it. So, after that process has completed its task, tsaka lang siya magiging available. Now, if we are to relate this on a call, like your cell phone, once a call is established, your process cannot preempt the ongoing conversation. Yung nagtatawagan has to voluntarily release the process. Hindi isisingit yung process mo. Kailangan mai-release mo muna nung unang mga processes if it is about a call. Now we have the concept of, next we have the concept of circular wait. Okay? So, if we have set of processes, meron kang P0, P1, and so on and so forth of waiting processes must exist such that P0 is waiting for a resource held by P1, P1 is waiting for a resource held by P2, and so on and so forth. So, therefore, it is the number of processes minus 1. So, kailangan may matapos muna siyang isang process. So, it's waiting for a resource held by the current resource, and that the processes is waiting for a resource held by the previous process. So, if we are to relate this again on a call sa cell phone, your process, which is calling your friend, will be held on circular wait until the resource, the communication link, will now be available. Okay, so just prepare your questions during our synchronous meeting. We have here an example. Okay, on the codes, we have the thread, and thread 1 attempts to acquire the mutex locks in the order. So we have mutex lock. First mutex, we have second mutex. So in first mutex and second mutex, thread 2 attempts to acquire the mutex in the order. So, second mutex, and first mutex. Dito sa illustration na to, there is a possibility of deadlock. Deadlock is possible if thread 1 acquires first mutex while thread 2 acquires the second mutex. So, just to give you an idea what a mutex is a binary variable whose purpose is to provide locking mechanism. It is used to provide mutual exclusion to a section of code, means only one process can work on a particular code section at a time. Even through deadlock, it is possible, it will not occur if thread 1 can acquire and release the mutex. So, first mutex and second mutex before thread 2 attempts to acquire the locks. And of course, the order in which the threads run depends on how they are scheduled by the CPU scheduler. So, yung kasunod na topic natin dito is the CPU scheduler. This example illustrates a problem with handling deadlocks. It is therefore difficult to identify and test for deadlocks that may occur only under certain circumstances. Okay, next. We have here the figure. Deadlocks can be described more precisely in terms of a directed graph. So, eto. This is a directed graph. This graph consists of a set of vertices and a set of edges. Okay, so the set of vertices V is partitioned into two different types of nodes. Like you have process P, ito, for process P, we have P1, P2, and P3. Okay, so the set consisting of all the active processes in the system. Next, we have the R. So in this case, we have R1, R3, R2, and R4. The set consisting of all resource types in the system. A directed edge from process PI to resource type RJ. So, halimbawa, meron po tayong sequence of resources. So, in a directed graph, if we have process here directed to a resource, we have a request edge. Okay, so it signifies that process has requested an instance of resource of that type and is currently waiting for that resource. A directed edge from resource type to process is denoted by ito, resource to process. It signifies that an instance of resource type has been allocated to process. So usually, we denote process through process iterations and of course the number of instances. So a directed edge from process to R is request edge, whereas if it is directed from an instance towards a process, we have now our assignment edge. Dalawang klase. So, request edge, process going to a resource instance. Assignment edge, that is from a resource, assigning this to a process. Since resource type may have more than one instance, we represent each such instance a dot within a rectangle. So, may figure. Tingnan natin sa figure, ha? So, ito. We have one instance for R1. Isang instance din ang binibigay ni resource 3. While on resource 2, we have 2 instances. Resource 4, we have 3 instances. Now, let's check on the figure here. Okay? Ano-ano po yung mga symbols na makikita natin? We represent each process as a circle. Ito, process for a circle. That's for a pie. And a resource type as a rectangle. So, ito si resource type. Makikita mo na naka-rectangle. Then, since resource type may have more than one instances, ito, isang instance, ito mga representations ng instances. So, there is a dot within a rectangle. A dot within a rectangle. Just like what we saw a while ago, we have this resource and then these are the instances. Now, in the third figure here, ito, P1 requests an instance of a resource in RJ. So, nagre-request siya ng instance on a resource RJ. In the fourth figure here, a process is holding an instance of a resource and only one instance of the 4 instances is requested. So, mayroon siyang 1, 2, 3, 4 instance. Isa lang yung kanyang na-hold na instance. So, these are the figures that you have to consider in an allocation graph. Now, let's try to check the figure here. The resource allocation graph shown in this figure are the following. Ano-ano mga situations? Let us define the process. We have how many processes? So, accordingly, titingnan natin sa figure, we have process 1, we have process 2, And we have process 3. Ilan ang instances? So, we have how many resources? 1, 2, 3, 4 resources. So, we have to list the resources. R1, we have R2, R3, and R4. Okay? Now, if we are to consider the edges, syempre on those resources, we have to consider these dots for the instances. One instance for resource R1, one instance for resource R3, two instances for resource 2, and there are 3 instances for resource 4. Now, for the edges, is equal to. So, we have P1, ito, of resource R1. Ito. Then we have process P2 on resource R3. P2 on resource R3. So we have okay, with the sets of processes, with the sets of resources, and the set of edges illustrated here, let us try to identify the process states. So, una, we have process P1. So, process P1 is holding an instance of resource type R2. Ito siya. It's holding an instance of resource type R2. And is waiting for an instance of resource type R1. Now, if we are to analyze process 2 is holding an instance of R1 and an instance of R2. Okay? Dalawa yung hinuhold niya, an instance of R1 and R2. And is waiting for an instance on resource 3. Si process 3 naman. Process 3 is holding an instance of R3. Okay? So that is our interpretation on the processes, the resources, and the edges. Okay, so suppose that process P3 requires an instance of resource type R2. P3 of resource type R2. So, since no resource instance is currently available, we add an edge P3 to R2. So, at this point, 2 minimal cycles exist in the system. So, we have 2 minimal cycles that exist in the system. Process P1, so process P1, process P2, and process P3 are deadlocked. Bakit? So, si process P2 is waiting for the resource type R3, which is held by process P3. Process P3 is waiting for either process P1 or process P2 to release resource 2. Okay? In addition, process P1 is waiting for a process to release the resource R1. So, given the condition of a resource allocation graph, it can be shown that if the graph contains no cycle, then no process in the system is deadlocked. If the graph, katulad nito, if the graph contains a cycle, then there is a deadlock. So, if each resource type has exactly one instance, then a cycle implies that a deadlock has occurred. If the cycle involves a set of resource types, each of which has only one single instance, then a deadlock has occurred. Each process involved in the cycle is deadlocked. Ito. Each process P1, process P2, is considered as deadlock. So, in the case In this case, the cycle in the graph is both a necessary and a sufficient condition for the existence of a deadlock. Now, consider this resource allocation graph. In this example, we also have a cycle. Let's try to check. So we have P1, okay. P1 is requesting an instance of resource R1. Next, we have P3. P3 is requesting an instance for resource R2. Then, resource R2 is currently held by process P1. We say that this is a cycle because we have here path that leads from process P1 and it will end to process P1. So it started with analyzing the path from P1, traversing this to these resources and nodes, and it will end to P1. So we have here a cycle. Okay. Though there is a cycle, however, there is no deadlock. Bakit kaya walang deadlock? Because in all the resources, there are two instances. Observe that process P4 may release its instance of resource type R2. That resource can be allocated to P3, breaking the cycle. So in summary, if a resource allocation graph does not have a cycle, then the system is not in a deadlock state. If there is a cycle, then the system may or may not be in a deadlocked state considering the instances of resources. This observation is important when we deal with the deadlock problem. So, titingnan lagi kung yung resources. So, kung meron namang dalawang resources and that they are not currently holding and waiting, so, maaaring hindi po siya magkakaroon ng deadlock. Okay, so just to review on the previous topics or the previous slides, we say that if a graph contains no cycles, no deadlock. If graph contains a cycle, however, ito po yung dalawang condition, kahit may cycle po siya, if only one instance per resource type, then there is deadlock. Pero, if there are several instances per resource type, possibly there is a deadlock. So, tinitingnan natin yung instances doon po sa mga resources. What are the different methods in handling deadlock? So, we can deal with deadlock problem in one of the three ways. We can use a protocol to avoid deadlock, ensuring that the system will never enter a deadlock state. Or, we can allow the system to enter a deadlock state, detect it, and recover. Or di kaya, we can ignore the problem altogether and pretend that deadlocks never occur in the system. Let us now discuss the different ways to prevent deadlock. First, we have the mutual exclusion. The mutual exclusion condition must hold. That is, at least one resource must be non-shareable. Shareable resources, in contrast, do not require mutually exclusive access and thus cannot be involved in a deadlock. Read-only files are a good example of a shareable resource. If several processes attempt to open a read-only file at the same time, that they can be granted simultaneously. A process never needs to wait for a shareable resource. So in general, we cannot prevent deadlocks by denying the mutual exclusion condition because some resources are non-shareable. For example, a call on your cell phone cannot be simultaneously shared by several callers. Isa lang ang pwedeng tumawag sa iyo at a time. How about hold and wait? So, to ensure that the hold and wait condition never occurs in the system, we must guarantee that Whenever a process requests a resource, it does not hold any other resources. One protocol that we can use requires each process to request and be allocated and all its resources before it begins execution. We can implement this provision by requiring that system calls requesting resources for a process will precede all other system calls. The third method of deadlock prevention is no preemption. No preemption of resources that have already been allocated. All processes have to voluntarily exit the resource before it can be available to the next process. So we have here the condition for no preemption. A circular wait is a way to ensure that this condition never holds. Circular wait imposes a total ordering of all the resource types and requires that each process requests on a resource. So it has to be in an increasingly order of enumeration. Now, to illustrate, we have to consider the different resource types. Say, for example, we have this drive. This drive is a resource. So we have 5 instances. This is equal to 5 instances. And then we have the printer. Printer will have 12 instances. Okay. So we compare 2 resources and we determine whether one precedes in the order. So mauuna muna si disk drive, then we have the printer. We define one-to-one function. So one-to-one function, if we have here the function of a disk drive, function of a printer, one-to-one function. And we have to consider the natural numbers for the instances. For example, if the set of resource type R includes disk drives and printers, then we have here the instances. F is defined as the function for each of these resource. So we can now consider the protocol to prevent deadlock. If we relate on the previous example, we have the disk drive and the printer. In this code, we assume that thread 1 is the first to acquire. So in this example, we have the first one to acquire the resource is first mutex, followed by the second mutex. In this relationship, the first mutex must acquire first the resource before it will be given to the second mutex. Next, we have here the illustration to assume a function that transfers funds between 2 accounts. Now, to prevent a race condition, each account has an associated mutex. So that is obtained from a getLock function. So we have the getLock function for the 2 activities, the account from and account to. Deadlock is possible if 2 threads simultaneously invoke the transaction. So if you transpose an account to prevent deadlock, one thread has to invoke first the account 2, then withdraw and deposit to the next account. So in this example, the sequence should be to withdraw first from an account, then deposit to an account. Next, we have the concept of the deadlock avoidance. This prevents deadlocks by limiting how requests can be made. The limits ensure that at least one of the necessary conditions for deadlock cannot occur. Possible side effects of preventing deadlocks by this method results to low device utilization and reduced system throughput. The various algorithms that use this approach differ in the amount and type of information required. The simplest and most useful model requires that each process declare the maximum number of resources of each type. So, given that there is a priori information, it is possible to construct an algorithm that ensures that the system will never enter a deadlock state. So there should be the maximum number of resources described on the priori. A deadlock avoidance algorithm examines the resource allocation state to ensure that a circular wait condition can never exist. So the resource allocation state is defined by the number of available and allocated resources and the maximum demands of the process. So we will be illustrating this in a safe state sequence. So those are the contents of the information that will be illustrated later on a table. On a safe state sequence, we say that a process requests an available resource. The system must decide if immediate allocation leaves the system in a safe state. So we have here the set of conditions. Now let me apply this in an example, and of course okay, let us now identify a safety state sequence. Safety state sequence. So ano po yung sequence so that we can avoid deadlock. This time we have to consider a single instance. Makapal itong instance. Try ko po. Okay. So, yung mga given, let's identify the set of given. Given is, we have, for the processes, we have 4 processes, and then on the instance, say we have 12. Okay, so let's illustrate the given on a table. Given that there are 4 processes, okay, so let's name the process to be process P1, process P2, process P3, and process P4. The given maximum need, max need for every process. Ito yung need nila. So, si P1, we have 8, then 9, 5, and 3. The current allocation for these processes, process P1 is currently allocated with 3 units. Then you have 4, 2, and 1. Okay, let's identify as to how many units left, and that will be used by these processes. So the total number of instances, number of 2P1. Okay, ito siya. So the current allocation of P1 is equal to 3, plus the available number of units is 2. It is equal to 5. So, ilan yung kailangan ni P1? 8. So, 5 is less than its maximum need. So, this has to wait. Next, ito naman tayo kay process P2. If 2 units is given to P2. So, the current allocation of P2 is 4. Plus available, which is equal to 2, that makes it 6. So, ilan yung kailangan niya? 9. So, with that, this process P2 has to wait. Okay. If 2 units is given to process 3, ilan yung current allocation ni process 3? It's 2 plus 2 units is equal to 4. 4 units. Ilan yung kailangan ni process P3? It's 5. Still, it is less than the maximum need. So, process P3 has to wait. Okay, next. If 2 units is given to process 4. So, process 4, current allocation is 1 plus the available 2 units, that it makes it 3. O, enough lang. So, the maximum need is equal to 3. With this, process 4 is complete. Okay? Check na po natin si process 4 because it's already complete. Next, syempre, we have to consider this algorithm here, it can wait until all processes have finished. So we have finished 4 processes, and this we will go back to process P1. Now, what is the current allocation? The current allocation is equal to 3. So if we are going to give this 3 units to P1, 3 units to P1. So how would we simulate this? P1 has a current allocation of 3. 3 plus 3 is equal to 6. Pwede na kaya? Hindi pa rin. Kasi 8 po yung maximum need ni P1. So still, this has to wait. Okay. Next, if, say, ibibigay po natin yung 3 units sa kasunod na process to process P2. What is the current allocation of process P2? 4 plus 3 is equal to 7. Still, process 2 has to wait. 9 lang or 9 ang kailangan niya, and this current available is 7. So again, mag-wait pa rin po si process P2. If 3 units will be given to process P3. So, ilan na yung current allocation ni process P3? 2 plus the available unit now is equal to 3. 2 plus 3 is equal to 5. Ilan yung kailangan ni process 3? So, it's 5. It's just enough that this will be accommodated. So, by this time, process P3 is complete. Okay? So, check na po natin si process P3. Sa algorithm, pabalik ulit tayo sa unfinished process. So, dito ko na lang ilalagay. Ito ay, yung ito yung kasunod niya dito. Okay? So, if, say, 3 units, if 3 units is given to process P1. Okay? Process P1. Tingnan natin. Okay, so in this stage, meron na po tayong additional, ito yung nai-release ni process P3. So kung ito yung nai-release ni process P3, therefore, i-update na po natin. So we have now the available 5 units. If 5 units is given to P1, okay, so ilan po yung allocation niya? 3 plus 5 is equal to 8. Okay, sa wakas, nagawa rin po si process P1. So, since the maximum need is 8 and we have available 8, so then this cycle, process P1 is complete. Okay, next, we have process 2. So, ilan na po yung nai-release ni process P1 nung na-complete siya? We have 8 units. So, we have 8 units to P2. So, ilan po yung current allocation ni P2? It's equal to 4 plus 8. This is equal to 12. So, at this cycle, process P2 is complete. So, check na po natin si process P2. So, we have just completed the 4 processes. Now, what is the safe state sequence? So, if we are to identify the sequence, yung first po na na-complete is process P4. So, therefore, we have to give the sequence now. It's safe to process P4 first, followed by process P3. So, we have process P3, followed by process P1, then lastly, we have P2. Okay? So, ito po yung safe state sequence. Para hindi magkaroon ng deadlock, we have to follow this sequence. Okay? So, that is for a single instance. Next, on your exercise, related to this given, I will be creating a link for your submission. So I will announce as to when are you going to submit this submission. Well, probably it is on our synchronous meeting. Okay, so on our example, if a system is in a safe state, then there is no deadlock. A while ago, we have illustrated a safe state sequence where the maximum need is accommodated by the available units. Therefore, there is no deadlock if it is a safe state. If a system is unsafe state, then there is a possibility of deadlock. So to avoid deadlock, what we did is we manage a safe state sequence. That is to ensure that the system will never enter an unsafe state. So avoidance in this implementation is a safe state sequence. Now to note, an unsafe state may lead to a deadlock state. As long as the state is safe, the operating system can avoid unsafe and deadlock states. Kaya we have to consider several algorithms to make the system safe. In an unsafe state, the operating system cannot prevent processes from requesting resources in such a way that a deadlock occurs. So the behavior of the process controls unsafe state. So we have to identify as to what are those behavior of these processes, and in consideration, we have the sequence of state safe. Okay, so we have the avoidance algorithm. Tapos na po natin ito ma-illustrate si single instance. Let's now have the multiple instances. Now, si multiple instances are illustrated through a banker's algorithm. Just to give you a background on what a banker algorithm is, the name is chosen because the algorithm could be used in banking system to ensure that the bank never allocated its available cash in such a way that it could no longer satisfy the need of all its customers. So sinisigurado ni bangko na enough yung kanyang kaperahan para ma-accommodate yung mga customers na nagta-transfer, nag-withdraw. So all these transactions can be accommodated na that the bank has to make sure na meron silang enough resources para sa mga customers. So what is the technique here? When a new process enters the system, it must declare the maximum number of instances of each resource type that it may need. So ikaw process 1, maximum na ibibigay ko sa iyo 8. Sabihin niya na, oh, ikaw process 2, maximum na pwede kong ibigay sa iyo is 5. So there is a priori, hindi yung only. So to manage this, the operating system has to consider a priori on the different instances of the process. This number may not exceed the total number of resources in the system. So when a user requests a set of resources, the system must determine whether the allocation of these resources will leave the system in a safe state. So if it will, the resources are allocated. Otherwise, the process must wait until some of the other processes releases the other resources. So several data structures must be maintained to implement that the banker's algorithm is established. These data structures encode the state of the resource allocation system. Okay, so yung mga mga basic concept. First, we have the claim edge. The request and assignment edges are considered previously. So if you have to consider a request edge, a process has to request an instance. So in an assignment edge, the resources is being accessed by a process. Now we have the concept of a claim edge. A claim edge means that a process may request a resource at some time in the future. So a process may request a resource or probably there are considerations of instances. Maring isa or maraming instances. So when a resource is released by process, the assignment edge is reconverted to a claim edge. Note that the resources must be claimed and that there is a priori in the system. That is, before a process starts its execution, all its claim edge must already appear in the resource allocation graph. Okay, so let's try to check this figure. Suppose that process requests a resource. Suppose that process requests a resource. The resource can be granted if converting the request edge like process to a resource with an assignment edge. So say process is requesting process resource in R1. So with this, we check for the safety by using a cycle detection algorithm. An algorithm for detecting a cycle in this graph requires an order of two operations, process P1 and process P2, where N is the number of processes in the system. If no cycle exists, then the allocation of the resource will leave the system in a safe state. If cycle is found, then the location will put the system in an unsafe state. So in this case, the process will have to wait to its request para masatisfy. So on this figure, meron po ba cycle? So if we have P1 to R2, dito yung cycle na hinto. So in this case, there is no cycle. Next, we have the unsafe state in resource allocation graph. Bakit kaya unsafe state po ito? Now let's check. If suppose P2 requests R2. If suppose that P2 requests R2. Although R2 is currently free, we cannot allocate this to P2 since this allocation will create a cycle in the graph. So kung ilalagay natin dito, i-request niya, that would mean a cycle on the graph. So a cycle, as mentioned, indicates that the system is unsafe state. So if P1 requests R2, then a deadlock occurs. So in this case, if say P1 requests R2 and P2 is currently holding an instance on R2, there occurs a deadlock and it is unsafe. The banker's algorithm. Suppose that process requests a resource. So the request can be granted only if converting the request edge to an assignment and that it does not result in the formation of a cycle. So titingnan po natin yung mga example. Una, tandaan po natin yung process on how to implement banker's algorithm. This is only intended for multiple instances. Like for example, you have process 1. So process 1 contains an instance of A, B, and C. So in a resource, this is R1, you have 3 instances. If this is process P1, then we have here the relationship to instances. Each process must have a priori claim on its maximum use. So, identify din natin yung column on its max use. And when a process requests a resource, it has to hold and wait. So, there are conditions. We have to set the condition. If it has to request a resource, siya po ba ay masiserve kaagad or it has to wait and hold until the maximum resource is allocated. When a process gets all its resources, it must return them in a finite amount of time. So remember the sequence that the moment you have to request for an instance, saka lang magagamit po yung ating mga resources. And the moment that it is used, the process has to release the resource. Let us now have the data structures for banking algorithms. This will be used especially on the illustration of the table. There are number of processes. So N will be the number of processes, P0, P1, P2, P3, and P4. And M is equal to the number of resource types. Like in a resource, for process P1, there are resource types A, B, and C. So available means these are the vector of length M. So sa table, makikita po natin na meron siyang available on different resources as this is being classified to the different instances on the resource. The maximum. So if you can recall the banker's algorithm na concept, si banker, ang kailangan niyang ibibigay sa mga processes, pwede nilang ibigay na mga instances are allowed kung siya ay mayroong enough resources to accommodate this. So, siya ang magbibigay ng maximum allowable instances. Si allocation, N times M matrix. So, yung process in consideration to the number of instances. Ang need naman, lagi yung condition natin, if the need is less than or equal to the work available. So, kung ang need niya will be satisfied, then it will be held as complete. Kung yung need niya ay hindi masatisfied, then it has to hold and wait. The need on the table later will be computed to the maximum na nandun sa table minus allocation. So, I'm just giving you ahead this different data structures because we'll be manipulating and we'll be using all these terms. Next, we have the safety algorithm. So, meron po tayong steps sa safety algorithm. We have to identify work and finish. So, if the work is always equal to available, if it is false, then you have to iterate until then that the number of instances will be accommodated. For if halimbawa the iteration is set to false, then you have to continue on iterating until the condition need is less than or equal to work will be satisfied. Then once it is satisfied, it's true, update the work. So, work plus allocation until then that the process is executed. If finished, then the condition is true to all set of resources. So, the system is safe, is on a safe state. So, kung ano yung mga na-identify na mga sequence where this condition need is less than or equal to work is satisfied, then isa-isahin po siya and identify the safe state. So, ito po yung mga processes na ating gagawin. So, if request is less than or equal to the need, then you go to the next step. Ibig sabihin, when I say next step, work plus allocation is updated. Otherwise, it will become false and you have to iterate again until it will become true. So, you have to consider the two conditions for number 1 and number 2. Then number 3, you have to allocate the requested resources to the next process by updating the work. So, we have available is equal to available minus request. Then on the allocation, the formula is allocation plus request for the need. Then yung need minus the request. So, identify natin yung safe state. We say that if the resources are allocated to a process, it is on a safe state. So, si algorithm will continue on iteration if it is not satisfied. Now, let's manipulate this on a table. Suppose we have 5 processes, namely process P0, P1, P2, P3, and P4 respectively. So, among the 5 processes, we have the instances. So, the instance is associated to A, B, and C. 10 units for A, 5 units for B, and 7 units for C. check natin kung ilan na po yung allocated for the processes. So we have 0, 2 plus 1 plus 2, this is 5. 1 plus 1 here, this is 2. So we have 7 for A. Ito yung allocated to these 5 processes. So i-minus na po natin yung na-allocate, that is 7 to 5. And that we can get the available resource. 7 minus 5 is equal to 2. 5 minus 2 is equal to 3. 10 minus 7 is equal to 3. So, ito na lang po yung available resource. The reason that we have it noted here. Okay. So, now, for us to identify the next sequence, for us to enumerate the safety safe sequence, given that we have 5 processes, first, kailangan natin yung need. Ilan ba ang kailangan ng mga processes para sila po ay ma-utilize, sila po ay makagamit ng resource. So, the formula for the need is max minus allocation. So, this minus allocation. So, for process P0, we have 7 minus 0 is equal to 7. 5 minus 1 is equal to 4. 3 minus 0 is equal to 3. So, that is for process P0. And then, we have process P1, 1, 2, 2. 6, 0, 0. We have 2, 1, 1. And then for process P4, 3 minus 2 is equal to 1. 3 minus 0 is equal to 3. You have 5 minus 0 is equal to 5. So this is the need for this set of processes. Okay, now let's check on how it is accommodated. Paano po yung safety state sequence. So, first, we have process P0. Ilan po yung need in process P0? It is 743. So, we have 743. Compare this to the available, kung kaya na po niyang i-accommodate. So, our available is 332. Check on the condition. Is 743 less than or equal to 332? So if it is false, you have to iterate this, well, hold and wait until we have enough available resources to accommodate 743. So let's proceed to the next process, which is process P1. Ang kailangan po ni process P1 is 122. Okay, is it less than or equal to available, which is 332? Yes. So, if the condition is false, you have to update work plus allocation. So, 332, ilan po yung allocation ni process P1? It is 200. So, we have 2, 3, 5. So, we have to update the process. The process P1 contains now an updated available resource 5, 3, 2. Okay? Since this is completed, yung 532 units will be released by process P1 kasi natapos na siya. And that will now be available to the next process. Yun yung na-release niya. Next, we have process P2. Ilan po yung need in process P2? It's 600. Is 600 less than 532? So in this case, it is equal to false. So this process P2 has to hold and wait. So let us now proceed to process P3. The need of process P3 is equal to 211. So now the condition would be is 211 less than or equal to 532. So if this is true, then we have to update work plus the allocation here. So the allocation for process P3 is 211. So plus 211. So this is 3743. So this is now the resource that will be released by process P3 because P3 is by now complete. So we have to update it here. We have 7, 4, 3. Okay? Next process. Si process P4. Ilan po na yung need ni process P4? That is 531. So, we have 531. Is 531 less than or equal to 743? If it is true, then we have to update 743 plus the allocation for process P4 is 002. So, plus 002. So, we have 3 plus 2 is equal to 5, 4 plus 0 is equal to 4, 7 plus 0 is equal to 7. So, we have 7, 4, 5. Okay? So, with this, we are done with the 4 processes. So, we'll now go back on the processes which is not yet complete. So, in this case, we have process P0, hindi pa tapos. Ito din, we have process P2. Okay, P0 and P2. So, let us now accommodate process P0. So, we have here process P0. Ilan po yung need ni process P0? It is 743. So, process P0, 743, and then our current available is 745. Is 743 less than or equal to 745? If it is true, then process P0 will be completed. So, the moment that it will be processed, we have to update now the allocation. So, 0, 1, 0 plus 0, 1, 0. So, we have 5, 5, 7, 5, 5. So, we have to update here in the next sequence. So, we have the current available. Ano pa yung hindi natin na process? We still have process P2. So, we have P2. Considering the need of process P2, which is equal to 600. So, we have 600. And in comparison to the current 755. So, is 600 less than or equal to 755? If it is true, then this will be held, and we have to update the current process. So we have now work plus the allocation for process P2. And process P2 is allocated to 302. So we have plus 302. 5 plus 7 is equal to 5 plus 2 is equal to 7. 5 plus 0 is equal to 5. And then we have 7 plus 3 is equal to 10. Okay? So, bumalik lang din po kung ilan yung na-allocate kanina. So, in our given, we have 10 units for A, 5 units for resource B, and then we have 7 instances for C. So, malalaman natin na tama po yung ating computation because this is our reference here. So, what is the implication if we have undergone all this process? Ibig sabihin, a deadlock can be avoided if we make use of the safety state sequence. So, and that, process po muna ni OSC process P1 followed by the process P3, yun yung kasunod na na-process, followed by process P4. After process P4, si process P0 yung ating na-process, process P0, and then lastly, we have process 2. Okay? So, ito po yung ating safety state sequence. So, it has to be P1 first, ito. Then, ito yung next na na-complete, P3. Then, you have process P4. Then, followed by the second iteration for P0. Then, dalawang beses din natin na-deploy si process P2. So, if we will be using this state sequence, the deadlock will be avoided. Okay. Next, just to check on the sequence, you can verify on this. So we have the need, which is considering the formula maximum minus allocation. And then the system is a safe state if we have the sequence P1, P3, P4, P0, and P2. So yan po yung ating result then a while ago. Now, this is your exercise. Okay? So this will be given on your synchronous meeting. So check the request if it is less than or equal to available. This time, you have to consider 102 on process P1. You have to consider 102 on process P1. The condition here, you have still on the previous example, this is the first natin, this is with reference on the previous example. Now, as you update and you consider all the sequence, you would get this updated table. So, this is your first activity for this example on multiple instances. Kanina, iba yung exercise sa single instance. That is the first. Ngayon, sa multiple instance, this is the first activity. So, this is your requirement to solve for this requirement. Then, number 2, number 3, number 4. Okay, this has to be supported with your answer. Next, we'll proceed to deadlock detection. Okay, so if a system does not employ either a deadlock prevention or a deadlock avoidance algorithm, then deadlock situation may occur. In this environment, the system has to provide an algorithm that examines the state of the system to determine whether a deadlock has occurred. Then, an algorithm to recover from the deadlock. So, again, on the deadlock detection, okay lang, tolerate that the system can enter a deadlock state. Then identify what are these steps or sequence with deadlock, and then recover the system from deadlock. So as long as there is that provision for the operating systems to detect a deadlock, then it can be recovered with the in-place solutions. So, ano yung in-place solutions? Those are the previous topic for the safety state. Also, we have to consider the single instance and multiple instance. If all resources have only one single instance, then we can define a deadlock detection algorithm that uses a variant of the resource allocation graph called a wait for graph. So we obtain this graph from the resource allocation graph by removing the resource nodes. So process lang yung i-consider natin and collapsing the appropriate edges. So we'll be applying this on the next topic for deadlock detection. In the same concept, yung may mga terms tayo na ginamit before on our safety state, we still be using the available. So what is the given instances minus the allocated resources, that would mean the available. Then the allocation that is allocated by the operating system to the different resources. And then considering the request, where we have the matrix that indicates the current the request. So tinitingnan natin kung ano po yung kanyang need over the available resource. So the detection algorithm is somehow very similar to the previous activity we have implementing banker's algorithm. So we have to consider the work and finish. So if the need is less than or equal to the current available, it is held as true, and that we have to update the work. So pag update natin ng work, it has to be deallocated and released to the next process. If it is false, it has to wait until the request is less than or equal to work. So there is an iteration here. And then, if ever na it will become true, update, work plus allocation. Ina-update po natin ito sa table. And if it is finished, ibig sabihin, lahat po ng mga processes are held by the operating system. Okay, algorithm requires an order of the operations to detect whether the system is in a deadlock state. Still, we'll be using the set of processes and instances. Okay, so in this example, it is given that we have 5 processes. So what are these 5 processes? P0, P1, P2, P3, and P4. Okay, so now we have the instances. 7 instances for A, 2 instances for B, and 6 instances for C. So, compute po natin yung ating allocation. So, we have 3 plus 1 plus 2. This is equal to 6. So, for B, we have 1 and 2. This is equal to 2. A, 2 plus 3 plus 2 is equal to 7 to 6. So, therefore, the allocation for all these 5 processes is now 726. Ilan po yung given? 726. So, 726 minus 726 is equal to 0, 0, 0. Ito po yung ating available. 0, 0, 0. So, if it is so, how are we going to identify the sequence in a way that all these processes can be accommodated by the system? Okay, let us start with process P0. P0 is request. So, ating kinokondisyon at tinitingnan natin condition lagi is if the request is less than or equal to work. Ito po yung sa algorithm. Now, if we are to supply the value for process P0, the request of process P0 is 0, 0, 0. And then, is it equal or less than to the available? The available work now is 0, 0, 0. Okay? So then, if it is true, in which, if we are to consider this condition is equal to true. So therefore, we have to add allocation to work. Work plus allocation. So, what is the allocation of process P0? 0, 1, 0. So we have to add it here. 0, 1, 0. So we have 0, 1, 0. This process will be released by process P0. P0 is completed. Okay, next. We have process P1. Ilan po yung request ni process P1? It's 202. Okay. Is 202 less than or equal to 010? Ito yung ating updated available resource. 010. So then, if it is false, therefore it has to wait. Let us proceed to process P2. Ilan po yung request ni process P2? P2 request 00. 000. Is 000 less than 010, which is available? Yes. So if it is true, we have to update the available. So hindi siya mag-wait. Instead, this will be completed since we have now to accommodate the allocation for process P2. It's true. So therefore, we have the allocation 3, 0, 3. 0 plus 3 is equal to 3. 1 plus 0 is equal to 1. 0 plus 3 is equal to 3. So this is now our available process to be released, the available resource to be released by process P2. Okay. So, anong kasunod siya sa process P2? So, meron tayo ditong complete. Ito din kanina. This is also complete. Next is process P3. Okay. So, si process P3, ilan po yung kanya nire-request? It's 100. 100. And our available is 313. Is 100 less than or equal to 313? So, if it is true, then this time, process 3 is complete. Okay? And we have to add the allocation for process P3. The allocation for process P3 is 211. So we have to add from here. We have 3 plus 1 is equal to 4. 1 plus 1 is equal to 2. 3 plus 2 is equal to 5. So we have the current available is now 524, which will be released by process P3. So dito ko na lang po idudugtong si process P4. Okay? So, ilan po yung request ni process P4? Process P4, yung request po niya is 002. So, 002 is less than or equal to the current available 524. So then, if it is true po ba? Yes, it's true. The system has enough resources to accommodate the request of process P4. This is therefore true, and if it is true, it is also complete. So we have to add now the allocation of process P4, which is 002. So ipa-plus na po natin dito. So we have 4 plus 2 is equal to 6. 5 plus 2 is equal to 2. Then we have 5 to 6. So with this cycle, si process P4 is already complete. So though we have finished until process P4, yet we have unfinished jobs for process P1. So P1 has to be considered now, and that there is 202 requests for process P1. So 202. And our available is 526. So let's compare. If is 202 less than or equal to 526, so this time it is true. Kaya na pong i-accommodate si process P1. We have enough resources. So therefore, if it is true, we have to add the allocation for process P1, which is 200. So we have plus 200. So 6 plus 0 is equal to 6. 2 plus 0 is equal to 2. We have 5 plus 2 is equal to 726. So again, the sequence is consistent with the instances on the given. So we have 726 here, we have 726. It means to say that all this sequence we have undergone is correct. So our goal is to prevent deadlock. So what would be the sequence of these 5 processes to avoid deadlock? So the sequence for this detection algorithm would be, you have to process first, process P0. Okay, ito. So, kasi on our simulation here, process P0 is accommodated. Next, after process P0, ano po yung na-complete? It is process P2. So, this becomes the next sequence. After process P2, P3 is also completed. After process P3, we deploy process P4 and it is also completed. So, this is next in the sequence. Now, since we have 2 iterations for process P1, yung unang deploy po natin, hindi siya kayang i-accommodate kasi there is no enough resources. However, we endure all these processes until we have enough resources for process P1. So, by this, yung pinaka-last, after the resource is deallocated by process P4, nagkaroon po ng available to accommodate this resources needed by process P1. So lastly, on the sequence is process P1. So this is the sequence for this detection algorithm. Okay, so we have the request for C. This is your Next exercise. So, meron po kayong tatlong exercise. Isang exercise para po doon sa ating single instance. Then, the second exercise was given on the banker's algorithm. And then, lastly, if P2 requests an additional instance of type C. So, you have to update now your system as to the request of P2. So, you have to consider here the given. I will be creating a link so that you can submit all these exercises. An announcement will be given to give you all these exercises. Okay, so wait for our synchronous meeting so that you can give your answers, but you have to compute ahead. Listen to this video and then compute for our given exercises, and that will be submitted once it is requested through a link in your announcement. Okay, so the detection algorithm, this is now the summary. When should we invoke the detection algorithm? So the answer depends on the two factors. Una, how often is a deadlock likely to occur? How many processes will be affected by deadlock when it happens? So if deadlock occur frequently, then the detection algorithm should be invoked frequently as well. Resources allocated to deadlocked processes will be idle until deadlock can be broken. So in addition, the number of processes involved in the deadlock cycle may grow. So deadlocks occur only when some processes makes a request that cannot be granted immediately. So the request may be the final request that completes a chain of waiting processes. We can invoke the deadlock detection algorithm every time a request for allocation cannot be granted. So in this case, we can identify not only the deadlocked set of processes, but also the specific process that caused the deadlock. So in reality, each of the deadlock processes is a link in the cycle in our resource graph. So all of them jointly caused the deadlock. Okay. Now, on the recovery from deadlock. So, ang pwede natin gawin would be these options. Abort all deadlock processes, abort one process, or di kaya we have to consider the order as what should or what process should we choose to abort. Okay, now further, we have the recovery. Paano po yung tatlong sistema na to? Okay, first, select a victim. Which resources and which processes are to be preempted? As in process termination, we must determine the order of preemption to minimize the cost. So, yung cost factors may include parameters as to the number of resources that a deadlock process is holding and the amount of time the process will consume. Next, babalik, roll back. So, if we preempt a resource from a process, what should be done with the process? So clearly, it cannot continue with its normal execution. So because it's missing some of the needed resource, we must roll back the process to some safe state and restart it from that state. So marami tayong pwedeng gawin na sequence, not only one sequence. Maaari we can explore on other sequence and that we can integrate a rollback. Next, we have starvation. How do we ensure that starvation will not occur? That is, how can we guarantee that resources will not always be preempted from the same process? So in a system where victim selection is based primarily on cost factors, it may happen that same process is always picked as a victim. So as a result, this process never completes its designated tasks. So there is a starvation on the selected process. So yung victim situation must address clearly that we must ensure that a process can be picked as a victim which has only small finite number of types. So the most common solution is to include the number of rollbacks in the cost factor. So pwede siyang balik-balik, and that we have to consider only small finite number of types. Now, to top it all, ano po yung mga pinag-usapan natin? So, a deadlock state occurs when two or more processes are waiting for an indefinite period for an event that can be caused only by one of the waiting process. So, kung wala po tayong problema sa processes, kaya po siyang i-accommodate because there are enough resources, then hindi po natin problema ito si deadlock chapter. Kaya lang, since there are limited resources at maraming processes ang kailangan, there would come a time that the system encounters deadlock. There are three principal methods for dealing with deadlocks. So we use some protocol to prevent or avoid deadlocks, ensuring that the system will never enter a deadlock state. So, una, sabi natin, ensure that the system will never enter a deadlock state. Pero, kung hindi kakayanin, go for the next. Allow system to enter a deadlock state. Detect and then recover. Or di kaya, ignore problem altogether and pretend that deadlocks never occur in the system na ginagamit ni maraming operating system because it's very seldom that deadlocks will occur. So, a solution is then use the detection algorithm. If ever there are occurrences of deadlock, then we have to recover the system with a different deadlock algorithm detection. So a deadlock can occur only if four necessary conditions hold simultaneously in the system, like meron tayong mutual exclusion, hold and wait, no preemption, and circular wait. So to prevent deadlocks, we can ensure that at least one of the necessary conditions never holds. So a method for avoiding deadlocks are preventing them requires that the operating systems have a priori information about how each processes will utilize system resources. The banker's algorithm, for example, requires a priori, which the information about the maximum number of each resources has to be identified first. So each process may request according to the identified available resources. Using this information, we can define a deadlock avoidance algorithm. So if a system does not employ a protocol to ensure that deadlocks will never occur, then a detection and recovery scheme may be employed. So a deadlock detection algorithm must be invoked to determine whether a deadlock has occurred. If a deadlock is detected, the system must recover either by terminating some of the deadlocked processes or by preempting the resources from some of the deadlocked processes. Where preemption is used to deal with deadlocks, three issues must be addressed. Yung pinaka-last topic po natin ito, that is selecting a victim, rollback, and starvation. In a system that selects victims for rollback primarily on the basis of cost factors, starvation may occur, and the selected processes can never complete the task. So therefore, programmers, researchers, yung mga ating experts, have to consider the basic approaches on the appropriate resource allocation problems in an operating systems. So the basic approaches can be considered, that is allowing us to select the optimal approach for each class resources in a system.